Okay, hi everybody, welcome back. Good to see you all here. Um, it's been another busy week of deep learning. Um, Lots of cool things going on, and like last week, I wanted to highlight a few really interesting articles that some of you folks have written. Um, Vitali wrote one of the best articles I've seen for a while, I think, actually talking about differential learning rates and stochastic gradient descent with restarts. Be sure to check it out if you can, because what he's done, I feel like he's done a great job of kind of positioning it in a place that you can get a lot out of it, regardless of your background. But for those who want to go further, he's also got links to like the academic papers it came from, and kind of graphs of showing examples of all of the things he's talking about. And I think it's a particularly nicely done article. So a good kind of role model for technical communication. One of the things I've liked about seeing people post these articles during the week is the discussion on the forums have also been like really great. There's been a lot of people helping out, like explaining things, which maybe there's parts of the post where people have said, actually, that's not quite how it works, and people have learnt new things that way. People have come up with new ideas as a result as well. These discussions of stochastic gradient descent with restarts and cyclical learning rates, there's been a few of them actually. Anand Sahar has written another great post talking about a similar topic and why it works so well. And again, lots of great pictures and references to papers and, most importantly, perhaps code showing how it actually works. Mark Hoffman covered the same topic at kind of a nice introductory level. I think really kind of clear intuition. Manikanta talked specifically about differential learning rates and why it's interesting. And again, providing some nice context to people not familiar with transfer learning, going right back to saying like, well, what is transfer learning? Why is that interesting? And given that, why could differential learning rates be helpful? And then one thing I particularly liked about Arjun's article was that he talked not just about the technology that we're looking at, but also talked about some of the implications, particularly from a commercial point of view. So thinking about like, based on some of the things we've learned about so far, what are some of the implications that has, in real life, and lots of background, lots of pictures, and then discussing some of the implications. So there's been lots of great stuff online, and thanks to everybody for all the great work that you've been doing. As we talked about last week, if you're kind of vaguely wondering about writing something, but you're feeling a bit intimidated about it because you've never really written a technical post before, just jump in. It's a really welcoming and encouraging group, I think, to work with. So we're going to have a kind of an interesting lesson today, which is we're going to cover a whole lot of different applications. So we've spent quite a lot of time on computer vision, and today we're going to try, if we can, to get through 3 totally different areas. Structured learning, so looking at kind of how you look at... So we're going to start out looking at structured learning or structured data learning, by which I mean building models on top of things that look more like database tables. So kind of columns of different types of data. They might be financial or geographical or whatever. We're going to look at using deep learning for language, natural language processing. And we're going to look at using deep learning for recommendation systems. And so we're going to cover these at a very high level, and the focus will be on here's how to use the software to do it, more than here is what's going on behind the scenes. And then the next 3 lessons will be digging into the details of what's been going on behind the scenes, and also coming back to looking at a lot of the details of computer vision that we kind of skipped over so far. So the focus today is really on like, how do you actually do these applications? And we'll kind of talk briefly about some of the concepts involved. Before we do, I did want to talk about one key new concept, which is dropout. And you might have seen dropout mentioned a bunch of times already and got the impression that this is something important, and indeed it is. So to look at dropout, I'm going to look at the dog breeds current Kaggle competition that's going on. And what I've done is I've gone ahead and I've created a pre-trained network as per usual, and I've passed in pre-compute equals true, and so that's going to pre-compute the activations that come out of the last convolutional layer. Remember, an activation is just a number, right? It's a number, just to remind you. An activation, like here is one activation, it's a number. And specifically, the activations are calculated based on some weights, also called parameters, that make up kernels or filters, and they get applied to the previous layer's activations, which could well be the inputs, or they could themselves be the results of other calculations. Okay, so when we say activation, keep remembering we're talking about a number that's being calculated. So we pre-compute some activations, and then what we do is we put on top of that a bunch of additional, initially randomly generated, fully connected layers. So we're just going to do some matrix multiplications on top of these, just like in our Excel worksheet. At the very end, we had this matrix that we just did a matrix multiplication by. So what you can actually do is if you just type the name of your learner object, you can actually see what's in it. You can see the layers in it. So when I've previously been skipping over a little bit about, oh, we add a few layers to the end, these are actually the layers that we add. We're going to do batch norm in the last lesson, so don't worry about that for now. A linear layer simply means a matrix multiply. Okay, so this is a matrix which has 1,024 rows and 512 columns. And so in other words, it's going to take in 1,024 activations and spit out 512 activations. Then we have a ReLU, which remember is just replace the negatives with 0. We'll skip over the batch norm. We'll come back to dropout. Then we have a second linear layer that takes those 512 activations from the previous linear layer and puts them through a new matrix multiply, 512 by 120, spits out a new 120 activations, and then finally put that through softmax. And for those of you that don't remember softmax, we looked at that last week. It's this idea that we basically just take the activation, let's say for dog, go e to the power of that, and then divide that into the sum of e to the power of all the activations. So that was the thing that adds up to 1, all of them add up to 1, and each one individually is between 0 and 1. Okay, so that's what we added on top, and that's the thing when we have pre-compute equals true, that's the thing we train. So I wanted to talk about what this dropout is and what this P is, because it's a really important thing that we get to tune. So a dropout layer with P equals 0.5 literally does this. We go over to our spreadsheet, and let's pick any layer with some activations, and let's say, okay, I'm going to apply dropout with a P of 0.5 to conv2. And what that means is I go through, and with a 50% chance, I pick a cell, right, pick an activation, so I pick like half of them randomly, and I delete them. Okay, that's what dropout is, right? So it's so the P equals 0.5 means what's the probability of deleting that cell, right? So when I delete those cells, if you have a look at the output, it doesn't actually change by very much at all. Just a little bit, particularly because remember it's going through a max pooling layer, right? So it's only going to change it at all if it was actually the maximum in that group of 4. And furthermore, it's just one piece of, if it's going into a convolution rather than into a max pool, it's just one piece of that filter. So interestingly, the idea of like randomly throwing away half of the activations in a layer has a really interesting result. And one important thing to mention is each mini batch, we throw away a different random half of activations in that layer. And so what it means is it forces it to not overfit, right? In other words, if there's some particular activation that's really learnt just that exact dog or that exact cat, right? Then when that gets dropped out, the whole thing now isn't going to work as well. It's not going to recognize that image, right? So it has to, in order for this to work, it has to try and find a representation that actually continues to work even as random half of the activations get thrown away every time, right? So it's I guess about 4 years old now, 3 or 4 years old, and it's been absolutely critical in making modern deep learning work. And the reason why is it really just about solved the problem of generalization for us. Before Dropout came along, if you tried to train a model with lots of parameters and you were overfitting, and you already tried all the data augmentation you could, and you already had as much data as you could, there were some other things you could try, but to a large degree you were kind of stuck, right? And so then Geoffrey Hinton and his colleagues came up with this dropout idea that was loosely inspired by the way the brain works, and also loosely inspired by Geoffrey Hinton's experience in bank teller queues, apparently. Somehow they came up with this amazing idea of like, hey, let's try throwing things away at random. And so, as you could imagine, if your P was like 0.01, then you're throwing away 1% of your activations for that layer at random. It's not going to randomly change things up very much at all. So it's not really going to protect you from overfitting much at all. On the other hand, if your P was 0.99, then that would be like going through the whole thing and throwing away nearly everything, right? And that would be very hard for it to overfit, so that would be great for generalization, but it's also going to kill your accuracy. So there's this kind of play-off between high p-values generalize well, but will decrease your training accuracy, and low p-values will generalize less well, but will give you a less good training accuracy. So for those of you that have been wondering, why is it that particularly early in training are my validation losses better than my training losses, right? Which seems otherwise really surprising. Hopefully some of you have been wondering why that is, because on a data set that it never gets to see, you wouldn't expect the losses to ever be much better. And the reason why is because when we look at the validation set, we turn off dropout, right? So in other words, when you're doing inference, when you're trying to say, is this a cat or is this a dog, we certainly don't want to be including random dropout there, right? We want to be using the best model we can. Okay, so that's why early in training, in particular, we actually see that our validation accuracy and loss tends to be better if we're using dropout. Okay, so yes, Annette, let me give you that.
Do you have to do anything to accommodate for the fact that you are throwing away some?
That's a great question. So we don't. But PyTorch does. So PyTorch behind the scenes does two things. If you say P equals 0.5, it throws away half of the activations, but it also doubles all the activations that are already there. So on average, the average activation doesn't change, which is pretty neat trick. So yeah, you don't have to worry about it. Basically, it's done for you. So if we say, so you can pass in P's, this is the P value for all of the added layers, to say with FastAI, what dropout do you want on each of the layers in these added layers? It won't change the dropout in the pre-trained network, like the hope is that that's already been pre-trained with some appropriate level of dropout, and we don't change it. But on these layers that we add, you can say how much. And so you can see here I said P's equals 0.5. So my first dropout has 0.5, my second dropout has 0.5. Right? And remember, coming to the input of this was the output of the last convolutional layer of the pre-trained network, and we go away and we actually throw away half of that before we even start, go through our linear layer, throw away the negatives, throw away half of the result of that, go through another linear layer, and then pass that to our softmax. For minor numerical precision reasons, it turns out to be better to take the log of the softmax than the softmax directly, and that's why you'll have noticed that when you actually get predictions out of our models, you always have to go np.exp of the predictions. But again, the details as to why aren't important. So if we want to try removing dropout, we could go p's equals 0, right? And you'll see whereas before we started with a 0.76 accuracy in the first epoch, now we've got a 0.8 accuracy in the first epoch, right? So by not doing dropout, our first epoch worked better, not surprisingly, because we're not throwing anything away. But by the third epoch, here we had 84.8, and here we have 84.1. So it started out better and ended up worse. So even after 3 epochs, you can already see we're massively overfitting, right? We've got 0.3 loss on the train and 0.5 loss on the validation. Okay. And so if you look now, you can see in the resulting model, there's no dropout at all. So if the p is 0, we don't even add it to the model. Another thing to mention is you might have noticed that what we've been doing is we've been adding 2 linear layers, right, in our additional layers. You don't have to do that, by the way. There's actually a parameter called extra fully connected layers that you can basically pass a list of how long do you want, or how big do you want each of the additional fully connected layers to be. And so by default, well, you need to have at least one, right? Because you need something that takes the output of the convolutional layer, which in this case is of size 1024, and turns it into the number of classes you have. Cats versus dogs would be 2, dog breeds would be 120, planet satellites 17, whatever. Right? So you always need one linear layer at least, and you can't pick how big that is. That's defined by your problem. But you can choose what the other size is, or if it happens at all. So if we were to pass in an empty list, then now we're saying don't add any additional linear layers, just the one that we have to have. Right? So here if we've got p's equals 0, extra fully connected layers is empty. This is like the minimum possible kind of top model we can put on top. And again, like if we do that, you can see above, we actually end up with, in this case, a reasonably good result because we're not training it for very long, and this particular pre-trained network is very well suited to this particular problem. Yes, Yunette?
So, Jeremy, what kind of P should we be using by default?
So the one that's there by default for the first layer is 0.25, and for the second layer is 0.5. That seems to work pretty well for most things, right? So like you don't necessarily need to change it at all. Basically, if you find it's overfitting, just start bumping it up. So try, first of all, setting it to 0.5. That'll set them both to 0.5. If it's still overfitting a lot, try 0.7. Like you can narrow down. And like there's not that many numbers to change, right? And if you're underfitting, then you can try making it lower. It's unlikely you would need to make it much lower because like even in these dogs versus cats situations, we don't seem to have to make it lower. So it's more likely you'll be increasing it to like 0.6 or 0.7. But you can fiddle around. I find the ones that are there by default seem to work pretty well most of the time. So one place I actually did increase this was in the dog breeds one. I did set them both to 0.5 when I used a bigger model. So like ResNet 34 has less parameters, so it doesn't overfit as much. But then when I started pumping it up to like a ResNet 50, which has a lot more parameters, I noticed it started overfitting. So then I also increased my dropout. So as you use like bigger models, you'll often need to add more dropout. Can you pass that over there, please, Yunette?
If we set P to 0.5, roughly what percentage? Is it 50%?
50%. Yep. Can you pass that back?
Thanks.
Is there a particular way in which you can determine if data is being overfitted?
Yeah. You can see that like here, you can see that the training error loss is much lower than the validation loss. You can't tell if it's like too overfitted. Like zero overfitting is not generally optimal. Like the only way to find that out is, remember, the only thing you're trying to do is to get this number low, right? The validation loss number low. So in the end, you kind of have to play around with a few different things and see which thing ends up getting the validation loss low. But you'll kind of get a feel over time for your particular problem. What does too much overfitting look like? Great. So that's dropout, and we're going to be using that a lot. And remember, it's there by default. Sorry, was there another question?
So I have two questions.
Sure.
One is, so when it says the dropout rate is 0.5, does it delete each cell with a probability of
Yes,
0.5, or
right.
does it just pick 50% randomly? I mean, I know both effectively
It's
and
the former. Yep.
Okay. Second question is, why does the average activation matter?
Well, it matters because remember, if you look at the Excel spreadsheet, that the result of this cell, for example, is equal to these 9 multiplied by each of these 9, right, and added up. So if we deleted half of these, then that would also cause this number to half, which would cause like everything else after that to change. And so if you change what it means, then you're changing something that used to say like, oh, fluffy ears are fluffy if this is greater than 0.6. Now it's only fluffy if it's greater than 0.3. Like you're changing the meaning of everything. So the goal here is to delete things without changing the meaning.
Why are you using linear activation for one of the earlier activations?
Why are we using linear?
Yeah, why that particular activation?
Because that's what this set of layers is. So the pre-trained network is the convolutional network, and that's pre-computed, so we don't see it. So what that spits out is a vector. So the only choice we have is to use linear layers at this point. Okay.
Can we have different level of dropout by layer?
Yes, absolutely.
And how to do that?
Great. So so you can absolutely have different dropout by layer, and that's why this is actually called P's. So you could pass in an array here. So if I went 0, 0.2, for example, and then extra fully connected, I might add 512. Right, then that's going to be 0 dropout before the first of them, and 0.2 dropout before the second of them. Thanks. Good question. And I must admit, I don't have a great intuition, even after doing this for a few years, for like when should earlier or later layers have different amounts of dropout. It's still something I kind of play with, and I can't quite find rules of thumb. So if some of you come up with some good rules of thumb, I'd love to hear about them. I think if in doubt, you can use the same dropout in every fully connected layer. The other thing you can try is often people only put dropout on the very last linear layer. So that'd be the two things to try.
So Jeremy, why do you monitor the loss, instead of the accuracy going up?
Well, because the loss is the only thing that we can see for both the validation set and the training set. So it's nice to be able to compare them. Also, as we'll learn about later, the loss is the thing that we're actually optimizing. So it's kind of a little more, it's a little easier to monitor that and understand what that means. Can you pass it over there?
So with dropout, we are kind of adding some random noise every iteration, right?
Yes.
So that means that we don't do as much learning, right? Or
yes.
should we? So
that's right.
So we have to play around with the learning rate, and
it doesn't seem to impact the learning rate enough that I've ever noticed it. I would say you're probably right in theory. It might, but not enough that it's ever affected me. Okay, so let's talk about this structured data problem. And so to remind you, we were looking at Kagel's Rossmann competition, which is a German chain of supermarkets, I believe. And you can find this in Lesson 3 Rossmann. And the main data set is the one where we were looking to say at a particular store, how much did they sell? Okay, and there's a few key pieces of information. One is what was the date. Another was were they open? Did they have a promotion on? Was it a holiday in that state? And was it a holiday for school, a state holiday there, or was it a school holiday there? And then we had some more information about stores, like what for this store, what kind of stuff did they tend to sell? What kind of store are they? How far away are the competition, and so forth. So with a data set like this, there's really two main kinds of column. There's columns that we think of as categorical. They have a number of levels. So the assortment column is categorical, and it has levels such as A, B, and C. Whereas something like competition distance, we would call continuous. It has a number attached to it where differences or ratios, even of that number, have some kind of meaning. And so we need to deal with these two things quite differently. Okay, so anybody who's done any machine learning of any kind will be familiar with using continuous columns. If you've done any linear regression, for example, you can just like multiply them by parameters, for instance. Categorical columns, we're going to have to think about a little bit more. We're not going to go through the data cleaning. We're going to assume that that's, and feature engineering, we're going to assume all that's been done. And so basically, at the end of that, we have a list of columns. And in this case, I didn't do any of the thinking around the feature engineering or data cleaning myself. This is all directly from the third place winners of this competition. And so they came up with all of these different columns that they found useful. And so you'll notice the list, here is a list of the things that we're going to treat as categorical variables. Numbers like year, month, and day, although we could treat them as continuous, like the differences between 2000 and 2003 is meaningful, we don't have to, right? And you'll see shortly how categorical variables are treated. But basically, if we decide to make something a categorical variable, what we're telling our neural net down the track is that for every different level of, say, year, 2000, 2001, 2002, you can treat it totally differently. Whereas if we say it's continuous, it's going to have to come up with some kind of like function, some kind of smooth-ish function, right? And so often, even for things like year that actually are continuous, but they don't actually have many distinct levels, it often works better to treat it as categorical. So another good example, day of week, right? So like day of week between 0 and 6, it's a number and it means something, like the difference between 3 and 5 is 2 days and has meaning. But if you think about like how would sales in a store vary by day of week, it could well be that like, Saturdays and Sundays are over here and Fridays are over here and Wednesdays are over here. Like each day is going to behave kind of qualitatively differently, right? So by saying this is a categorical variable, as you'll see, we're going to let the neural net do that, right? So this thing where we say which are continuous and which are categorical, to some extent, this is a modeling decision you get to make. Now, if something is coded in your data as like A, B, and C, or, Jeremy and Yannette, or whatever, you're going to have to call that categorical, right? There's no way to treat that directly as a continuous variable. On the other hand, if it starts out as a continuous variable, like age or day of week, you get to decide whether you want to treat it as continuous or categorical. Okay, so to summarize, If it's categorical in the data, it's going to have to be categorical in the model. If it's continuous in the data, you get to pick whether to make it continuous or categorical in the model. So in this case, again, I just did whatever the third place winners of this competition did. These were the ones that they decided to use as categorical. These were the ones they decided to use as continuous. And you can see that basically the continuous ones are all of the ones which are actual floating point numbers. Like competition distance actually has a decimal place to it, right? And temperature actually has a decimal place to it. So these would be very hard to make categorical because they have many, many levels, right? Like if it's like 5 digits of floating point, then potentially there will be as many levels as there are rows. Right? And by the way, the word we use to say how many levels are in a category, we use the word cardinality. Right? So if you hear me say cardinality, for example, the cardinality of the day of week variable is 7, because there are 7 different days of the week.
Do you have a heuristic for when to bin continuous variables, or do you ever bin variables?
I don't ever bin continuous variables. So one thing we could do with like max temperature is group it into 0 to 10, 10 to 20, 20 to 30, and then call that categorical. Interestingly, a paper just came out last week in which a group of researchers found that sometimes binning can be helpful. But that literally came out in the last week, and until that time, I haven't seen anything in deep learning saying that. So I haven't looked at it myself. Until this week, I would have said it's a bad idea. Now I have to think differently, I guess. Maybe it is sometimes.
So if you're using year as a category, what happens when you run the model on a year it's never seen? So you trained it in 2017.
We'll get there. Okay. Yeah. The short answer is it'll be treated as an unknown category. And so pandas, which is the underlying data frame thing we're using with categories, has a special category called unknown. And if it sees a category it hasn't seen before, it gets treated as unknown. So for our deep learning model, unknown will just be another category.
If our training data set doesn't have a category and the test has unknown, how will it treat?
It'll just be part of this unknown category.
Will it still predict?
It'll predict something, right? Like it'll just have the value 0 behind the scenes. And if there's been any unknowns of any kind in the training set, then it'll have learned a way to predict unknown. If it hasn't, it's going to have some random vector. And so that's an interesting detail around training that we probably won't talk about in this part of the course, but we can certainly talk about on the forum. Okay, so we've got our categorical and continuous variable lists defined. In this case, there was 800,000 rows, so 800,000 dates, basically, by stores. And so you can now take all of these columns, loop through each one, and replace it in the data frame with a version where you say, take it and change its type to category. Okay? And so that's just a pandas thing. So I'm not going to teach you pandas. There's plenty of books, particularly Wes McKinney's book on Python for data analysis is great. But hopefully it's intuitive as to what's going on, even if you haven't seen the specific syntax before. So we're going to turn that column into a categorical column. And then for the continuous variables, we're going to make them all 32-bit floating point. And for the reason for that is that PyTorch expects everything to be 32-bit floating point. Okay? So like some of these include like 1, 0 things like I can't see them straight away, but anyway, some of them are like was there a promo, was it a holiday, and so that'll become the floating point values 1 and 0, for instance. Okay, so I try to do as much of my work as possible on small data sets. For when I'm working with images, that generally means resizing the images to like 64 by 64 or 128 by 128. We can't do that with structured data, so instead I tend to take a sample. So I randomly pick a few rows. So I start running with a sample, and I can use exactly the same thing that we've seen before for getting a validation set. We can use the same way to get some random row numbers to use in a random sample. Okay, so this is just a bunch of random numbers. And then, okay, so that's going to be a size 150,000 rather than 840,000. And so my data, before I go any further, it basically looks like this. You can see I've got some Booleans here. I've got some integers here of various different scales. Here's my year, 2014. And I've got some letters here. So even though I said, please call that a pandas category, pandas still displays that in the notebook as strings, right? It's just stored in internally differently. So then the FastAI library has a special little function called process data frame. And process data frame takes a data frame and you tell it, what's my dependent variable, right? And it does a few different things. The first thing is it pulls out that dependent variable and puts it into a separate variable, okay? And deletes it from the original data frame. So DF now does not have the sales column in, whereas Y just contains the sales column. Something else that it does is it does scaling. So neural nets really like to have the input data to all be somewhere around 0 with a standard deviation of somewhere around 1. Right? So we can always take our data and subtract the mean and divide by the standard deviation to make that happen. So that's what do scale equals true does. And it actually returns a special object which keeps track of what mean and standard deviation did it use for that normalizing. So you can then do the same thing to the test set later. It also handles missing values. Missing values in categorical variables just become the ID 0, and then all the other categories become 1, 2, 3, 4, 5 for that categorical variable. For continuous variables, it replaces the missing value with the median and creates a new column that's a Boolean and just says, is this missing or not? And I'm going to skip over this pretty quickly because we talk about this in detail in the machine learning course. Okay, so if you've got any questions about this part, that would be a good place to go. It's nothing deep learning specific there. So you can see afterwards, year 2014, for example, has become year 2, okay, because these categorical variables have all been replaced with contiguous integers starting at 0. Right? And the reason for that is later on, we're going to be putting them into a matrix, right? And so we wouldn't want the matrix to be 2014 rows long when it could just be 2 rows long. Okay? So that's the basic idea there. And you'll see that the AC, for example, has been replaced in the same way with 1 and 3. Okay, so we now have a data frame which does not contain the dependent variable and where everything is a number. Okay, and so that's where we need to get to do deep learning, and all of the stage above that, as I said, we talk about in detail in the machine learning course. Nothing deep learning specific about any of it. This is exactly what we throw into our random forests as well. So another thing we talk about a lot in the machine learning course is validation sets. In this case, we need to predict the next 2 weeks of sales, right? It's not like pick a random set of sales, but we have to pick the next 2 weeks of sales. That was what the Kaggle competition folks told us to do. And therefore, I'm going to create a validation set, which is the last 2 weeks of my training set, right, to try and make it as similar to the test set as possible. And we just posted, actually, Rachel wrote this thing last week about creating validation sets. So if you go to fast.ai, you can check that out. We'll put that in the lesson wiki as well. But it's basically a summary of a recent machine learning lesson that we did. The videos are available for that as well, and this is kind of a written summary of it. Okay. So Rachel and I spent a lot of time thinking about kind of, how do you need to think about validation sets and training sets and test sets and so forth, and that's all there. But again, nothing deep learning specific, so let's get straight to the deep learning action. Okay. So in this particular competition, as always with any competition or any kind of machine learning project, you really need to make sure you have a strong understanding of your metric. How are you going to be judged here? And in this case, Kaggle makes it easy. They tell us how we're going to be judged. And so we're going to be judged on the root mean squared percentage error, right? So we're going to say like, oh, you predicted 3. It was actually 3.3. So you were 10% out. And then we're going to average all those percents, right? And remember, I warned you that you are going to need to make sure you know logarithms really well, right? And so in this case, we're basically saying your prediction divided by the actual, the mean of that, right, is the thing that we care about. And so we don't have a metric in PyTorch called root mean squared percent error. We could actually easily create it, by the way. If you look at the source code, you'll see like it's a line of code. But easier still would be to realize that that if you have that, right, then you could replace A with like log of A dash and B with like log of B dash, and then you can replace that whole thing with a subtraction. That's just the rule of logs, right? And so if you don't know that rule, then make sure you go look it up because it's super helpful. But it means in this case, all we need to do is to take the log of our data, which I actually did earlier in this notebook. And when you take the log of the data, getting the root mean squared error will actually get you the root mean squared percent error for free. Okay. But then when we want to like print out our root mean squared percent error, we actually have to go e to the power of it again, right? And then we can actually return the percent difference. So that's all that's going on here. It's, again, not really deep learning specific at all. So here we finally get to the deep learning. All right. So as per usual, like you'll see, everything we look at today looks exactly the same as everything we've looked at so far, which is first we create a model data object, something that has a validation set, training set, and optional test set built into it. From that, we will get a learner. We will then optionally call learner.lrfind. We'll then call learner.fit. It'll be all the same parameters and everything that you've seen many times before. Okay. So the difference, though, is obviously we're not going to go image classifier data dot from CSV or dot from paths. We need to get some different kind of model data. And so for stuff that is in rows and columns, we use columnar model data. Okay. But this will return an object with basically the same API that you're familiar with. And rather than from paths or from CSV, this is from data frame. Okay. So this gets past a few things. The path here is just used for it to know where should it store like model files or stuff like that. Right? This is just basically saying where do you want to store anything that you save later. This is the list of the indexes of the rows that we want to put in the validation set, which we created earlier. Here's our data frame. Okay. And then let's have a look. Here's this is where we did the log, right? So I took the y that came out of procdf, our dependent variable. I logged it, and I call that yl. Right? So we tell it when we create our model data, we need to tell it that's our dependent variable. Okay, so far we've got list of the stuff to go in the validation set, which is what's our independent variables, what's our dependent variables, and then we have to tell it which things do we want treated as categorical, right? Because remember, by this time, everything's a number, right? So it could do the whole thing as if it's continuous. It would just be totally meaningless, right? So we need to tell it which things do we want to treat as categories. And so here we just pass in that list of names that we used before. Okay? And then a bunch of the parameters are the same as the ones you're used to. For example, you can set the batch size here. So after we do that, we've got a standard model data object. There's a train DL attribute, there's a val_dl attribute, a train ds attribute, a val_ds attribute. It's got a length. It's got all the stuff exactly like it did in all of our image-based data objects. Okay, so now we need to create the model, or create the learner. And so to skip ahead a little bit, we're basically going to pass in something that looks pretty familiar. We're going to be saying from our model data, create a learner that is suitable for it, and we'll basically be passing in a few other bits of information, which will include how much dropout to use at the very start, how many activations to have in each layer, how much dropout to use at the later layers. But then there's a couple of extra things that we need to learn about, and specifically, it's this thing called embeddings. So this is really the key new concept we have to learn about. All right. So all we're doing basically is we're going to take let's forget about categorical variables for a moment and just think about the continuous variables. Right? For our continuous variables, all we're going to do is we're going to grab them all. Okay, so for our continuous variables, we're basically going to say, like, okay, here's a big list of all of our continuous variables, like the minimum temperature and the maximum temperature and the distance to the nearest competitor and so forth, right? And so here's just a bunch of floating point numbers. And so basically what the neural net's going to do is it's going to take that 1D array or vector, or to be very DL-like, rank 1 tensor, all means the same thing. Okay, so we're going to take our rank 1 tensor and let's put it through a matrix multiplication. So let's say this has got, like, I don't know, 20 continuous variables, and then we can put it through a matrix which must have 20 rows. That's how matrix multiplication works. And then we can decide how many columns we want, right? So maybe we decided 100, right? And so that matrix multiplication is going to spit out a new length 100 rank 1 tensor. Okay, that's what a matrix product does, and that's the definition of a linear layer in deep learning. Okay, and so then the next thing we do is we can put that through a ReLU, right? Which means we throw away the negatives. Okay, and now we can put that through another matrix product. Okay, so this is going to have 100 rows by definition, and we can have as many columns as we like. And so let's say maybe this was the last layer, so the next thing we're trying to do is to predict sales. So there's just one value we're trying to predict for sales, so we could put it through a matrix product that just had one column, and that's going to spit out a single number. Right? So that's kind of like a one-layer neural net, if you like. Now, in practice, we wouldn't make it one layer, so we'd actually have maybe we'd have 50 here, and so then that gives us a 50 long vector, and then maybe we then put that into our final 50 by 1, and that spits out a single number. And one reason I wanted to change that there was to point out, ReLU, you would never put ReLU in the last layer. Like, you'd never want to throw away the negatives, because the softmax, let's go back to the softmax. The softmax needs negatives in it, because it's the negatives that are the things that allow it to create low probabilities. That's minor detail, but it's useful to remember. Okay, so basically, a simple view of a fully connected neural net is something that takes in as an input a rank 1 tensor. It spits it through a linear layer, an activation layer, another linear layer, a softmax, and that's the output. Okay? And so we could obviously decide to add more linear layers. We could decide maybe to add dropout, right? So these are some of the decisions that we get to make, right? But there's not that much we can do, right? There's not much really crazy architecture stuff to do. So when we come back to image models later in the course, we're going to learn about all the weird things that go on in like ResNets and inception networks and blah, blah, blah. But in these fully connected networks, they're really pretty simple. They're just interspersed linear layers, that is matrix products, and activation functions like ReLU and a softmax at the end. And if it's not classification, which actually ours is not classification, in this case we're trying to predict sales, there isn't even a softmax. Right? We don't want it to be between 0 and 1. Okay? So we can just throw away the last activation altogether. If we have time, we can talk about a slight trick we can do there, but for now we can think of it that way. So that was all assuming that everything was continuous. Right? But what about categorical? Right? So we've got like day of week. Right? And we're going to treat it as categorical, right? So it's like Saturday, Sunday, Monday, that should be 6, Friday. Okay, how do we feed that in? Because I want to find a way of getting that in so that we still end up with a rank 1 tensor of floats. And so the trick is this. We create a new little matrix with 7 rows, and as many columns as we choose, right? So let's pick 4, right? So here's our 7 rows and 4 columns, right? And basically what we do is, let's add our categorical variables to the end. So let's say the first row was Sunday, right? Then what we do is we do a lookup into this matrix. And we say, oh, here's Sunday. We do a lookup into here, and we grab this row. And so this matrix we basically fill with floating point numbers. So we're going to end up grabbing a little subset of 4 floating point numbers. It's Sunday's particular 4 floating point numbers. And so that way we convert Sunday into a rank 1 tensor of 4 floating point numbers. And initially those 4 numbers are random. Right? And in fact, this whole thing, we initially start out random. Okay? But then we're going to put that through our neural net, right? So we basically then take those 4 numbers and we remove Sunday, and instead we add our 4 numbers on here, right? So we've turned our categorical thing into a floating point vector, right? And so now we can just put that through our neural net, just like before, and at the very end we find out the loss, and then we can figure out which direction is down and do gradient descent in that direction, and eventually that'll find its way back to this little list of 4 numbers, and it'll say, okay, those random numbers weren't very good, this one needs to go up a bit, that one needs to go up a bit, that one needs to go down a bit, that one needs to go up a bit, and so we'll actually update our original, those 4 numbers in that matrix. And we'll do this again and again and again, and so this matrix will stop looking random, and it will start looking more and more like the exact 4 numbers that happen to work best for Sunday, the exact 4 numbers that happen to work best for Friday, and so forth. And so in other words, this matrix is just another bunch of weights in our neural net, right? And so matrices of this type are called embedding matrices. So an embedding matrix is something where we start out with an integer between 0 and the maximum number of levels of that category. We literally index into a matrix to find a particular row. So if it was the level was 1, we take the first row, we grab that row, and we append it to all of our continuous variables. And so we now have a new vector of continuous variables. And then we can do the same thing for, let's say, zip code, right? So we could have an embedding matrix. Let's say there are 5,000 zip codes. It would be 5,000 rows long, as wide as we decide. Maybe it's 50 wide. And so we'd say, okay, here's 94003. That zip code is index number 4 in our matrix. So we'd go down and we'd find the 4th row. We'd grab those 50 numbers and append those onto our big vector. And then everything after that is just the same. We just put it through our linear layer, ReLU, linear layer, whatever. Okay.
What are those 4 numbers represent?
That's a great question. And we'll learn more about that when we look at collaborative filtering. For now, they represent no more or no less than any other parameter in our neural net. They're just parameters that we're learning that happen to end up giving us a good loss. We will discover later that these particular parameters often, however, are human interpretable and can be quite interesting. But that's a side effect of them. It's not fundamental. They're just 4 random numbers for now that we're learning, or sets of 4 random numbers.
Do you have a good heuristic for the dimensionality of the embedding matrix? So why 4 here?
I sure do.
But wait, there's more.
So what I first of all did was I made a little list of every categorical variable and its cardinality. Okay, so there they all are. So there's 1,000 plus different stores, apparently, in Rossmann's network. There are 8 days of the week. That's because there are 7 days of the week plus 1 left over for unknown. Even if there were no missing values in the original data, I always still set aside 1 just in case there's a missing or an unknown or something different in the test set. Again, 4 years, but there's actually only 3 plus room for an unknown and so forth. Right? So what I do, my rule of thumb is this. Take the cardinality of the variable, divide it by 2, but don't make it bigger than 50. Okay, so these are my embedding matrices. So my store matrix, so there has to have 1,116 rows, because I need to look up, right, to find here's store number 3. And then it's going to return back a rank 1 tensor of length 50. Day of week, it's going to look up into which one of the 8 and return the thing of length 4.
So would you typically build an embedding matrix for each categorical feature?
Yes.
Okay.
Yeah, so that's what I've done here. So I've said for C in categorical variables, see how many categories there are. And then for each of those things, create one of these. And then this is called embedding sizes. And then you may have noticed that that's actually the first thing that we pass to getLearner. And so that tells it for every categorical variable, that's the embedding matrix to use for that variable. Just behind you, there's... Yes, sure.
I have a question. So besides random initialization, are there other ways to actually initialize embedding?
Yes and no. There's 2 ways. One is random, the other is pre-trained. And we'll probably talk about pre-trained more later in the course. But the basic idea, though, is if somebody else at Rossmann had already trained a neural net, just like you would use a pre-trained net from ImageNet to look at pictures of cats and dogs, if somebody else has pre-trained a network to predict cheese sales in Rossmann, you may as well start with their embedding matrix of stores to predict liquor sales in Rossmann. And this is what happens, for example, at Pinterest and Instacart. They both use this technique. Instacart uses it for routing their shoppers. Pinterest uses it for deciding what to display on a web page when you go there. And they have embedding matrices of products, in Instacart's case of stores, that get shared in the organization so people don't have to train new ones.
So for the embedding size, why wouldn't you just use like the one hot scheme and just what is the advantage of doing this as opposed to just doing a one hot?
Yeah, good question. So we could easily, as you point out, have instead of passing in these 4 numbers, we could instead have passed in 7 numbers all zeros, but one of them is a 1. And that also is a list of floats. And that would totally work. And that's how, generally speaking, categorical variables have been used in statistics for many years. It's called dummy variable coding. The problem is that in that case, the concept of Sunday could only ever be associated with a single floating point number, right? And so it basically gets this kind of linear behavior. It says like Sunday is more or less of a single thing. Yeah, well, it's not just interactions. It's saying like now Sunday is a concept in 4-dimensional space, right? And so what we tend to find happen is that these embedding vectors tend to get these kind of rich semantic concepts. So, for example, if it turns out that weekends kind of have a different behavior, you'll tend to see that Saturday and Sunday will have like some particular number higher. Or more likely, it turns out that certain days of the week are associated with higher sales of certain kinds of goods that you kind of can't go without. I don't know, like gas or milk, say. Whereas there might be other products like wine, for example, like wine that tend to be associated with like the days before weekends or holidays, right? So there might be kind of a column which is like, to what extent is this day of the week kind of associated with people going out, you know? So basically, yeah, by having this higher dimensionality vector rather than just a single number, it gives the deep learning network a chance to learn these rich representations. And so this idea of an embedding is actually what's called a distributed representation. It's kind of the most fundamental concept of neural networks. It's this idea that a concept in a neural network has a kind of a high dimensional representation. And often it can be hard to interpret because the idea is like each of these numbers in this vector doesn't even have to have just one meaning. You know, it could mean one thing if this is low and that one's high, and something else if that one's high and that one's low, because it's going through this kind of rich nonlinear function, right? And so it's this rich representation that allows it to learn such interesting relationships. I'm kind of I've got another question. Sure.
All right, I'll speak louder. So are there is an embedding? So I get the fundamental of the word to vector algebra you can run on this thing. But are the embeddings suitable for certain types of variables, like? Or are these only suitable for, are there different categories that the embeddings are suitable for?
An embedding is suitable for any categorical variable.
Okay.
So the only thing it can't really work well at all for would be something that is too high cardinality. So like, in other words, we had like, whatever it was, 600,000 rows. If you had a variable with 600,000 levels, that's just not a useful categorical variable. You could bucketize it, I guess. Okay. But yeah, in general, like you can see here, the third place getters in this competition really decided that everything that was not too high cardinality, they put them all as categorical variables. And I think that's a good rule of thumb. You know, if you can make it a categorical variable, you may as well, because that way it can learn this rich distributed representation, whereas if you leave it as continuous, you know, the most it can do is to kind of try and find a single functional form that fits it well.
I have a question. So you were saying that you are kind of increasing the dimension, but actually in most cases we will use a one-hot encoding, which has even a bigger dimension. So in a way you are also reducing it, but in a most rich way.
I think that's fair, Yanet. Yeah, yes, you know, you can think of it as a one-hot encoding, which actually is high-dimensional, but it's not meaningfully high-dimensional because everything except 1 is a 0.
I'm saying that also because even this will reduce the amount of memory and things like this that you have to.
Right.
In practical terms, this is better.
You're absolutely right. You're absolutely right. And so we may as well go ahead and actually describe like what's going on with the matrix algebra behind the scenes. If this doesn't quite make sense, you can kind of skip over it, but for some people, I know this really helps. If we started out with something saying this is Sunday, right, we could represent this as a one-hot encoded vector, right? And so Sunday, maybe was position here, so that would be a 1, and then the rest are zeros. Okay, and then we've got our embedding matrix, right, with 8 rows, and in this case, 4 columns. One way to think of this actually is a matrix product, right? So I said you could think of this as like looking up the number 1, and finding like its index in the array. But if you think about it, that's actually identical to doing a matrix product between a one-hot encoded vector and the embedding matrix. Like you're going to go 0 times this row, 1 times this row, 0 times this row. And so it's like a one-hot embedding matrix product is identical to doing a lookup. And so some people in the bad old days actually implemented embedding matrices by doing a one-hot encoding and then a matrix product. And in fact, a lot of like machine learning methods still kind of do that. But as Yannette was kind of alluding to, that's terribly inefficient. So all of the modern libraries implement this as take an integer and do a lookup into an array. But the nice thing about realizing that it's actually a matrix product mathematically is it makes it more obvious how the gradients are going to flow. So when we do stochastic gradient descent, we can think of it as just another linear layer. Okay, so as I say, that's like a somewhat minor detail, but hopefully for some of you it helps.
Could you touch on using dates and times as categoricals and how that affects seasonality?
Yeah, absolutely. That's a great question. Did I cover dates at all last week? I don't remember. No? Great. So I covered dates in a lot of detail in the machine learning course, but it's worth briefly mentioning here. There's a FastAI function called addDatePart, which takes a data frame and a column name. That column name needs to be a date. It removes, unless you've got drop equals false, it optionally removes the column from the data frame and replaces it with lots of columns representing all of the useful information about that date, like day of week, day of month, month of year, is it the start of a quarter, is it the end of a quarter, basically everything that pandas gives us. And so that way we end up, when we look at our list of features, well, you can see them here, right? Year, month, week, day of week, etc. So these all get created for us by addDatePart. So we end up with, this 8 long embedding matrix. So 8 rows by 4 column embedding matrix for day of week. And conceptually, that allows us, or allows our model, to create some pretty interesting time series models. Right? Like it can, if there's something that has a 7-day period cycle that kind of goes up on Mondays and down on Wednesdays, but only for dairy and only in Berlin, it can totally do that. Right? It has all the information it needs to do that. So this turns out to be a really fantastic way to deal with time series. So I'm really glad you asked the question. You just need to make sure that the cycle indicator in your time series exists as a column. So if you didn't have a column there called day of week, it would be very, very difficult for the neural network to somehow learn to do like a divide mod 7 and then somehow look that up in an embedding matrix. Like it, not impossible, but really hard. It would use lots of computation, wouldn't do it very well. So an example of the kind of thing that you need to think about might be holidays, for example, or if you were doing something in of sales of beverages in San Francisco, you probably would want a list of like when is the ball game on at AT&T Park, right? Because that's going to impact how many people are drinking beer in Soma, right? So you need to make sure that the kind of the basic indicators or periodicities or whatever are there in your data, and as long as they are, the neural net's going to learn to use them. So I'm kind of trying to skip over some of the non-deep learning parts. All right, so the key thing here is that we've got our model data that came from the data frame. We tell it how big to make the embedding matrices. We also have to tell it of the columns in that data frame, how many of those are categorical variables or how many of them are continuous variables. So the actual parameter is number of continuous variables. So you can see we just pass in how many columns are there minus how many categorical variables are there. So then that way the neural net knows how to create something that puts the continuous variables over here and the categorical variables over there. The embedding matrix has its own dropout, right? So this is the dropout that's applied to the embedding matrix. This is the number of activations in the first linear layer, the number of activations in the second linear layer, the dropout in the first linear layer, the dropout for the second linear layer. This bit we won't worry about for now. And then finally is how many outputs do we want to create? Okay, so this is the output of the last linear layer. And obviously it's 1 because we want to predict a single number, which is sales. Okay, so after that, we now have a learner where we can call LR_find, and we get the standard looking shape, and we can say what amount do we want to use, and we can then go ahead and start training using exactly the same API we've seen before. So this is all identical. You can pass in, I'm not sure if you've seen this before, custom metrics. What this does is it just says, please print out a number at the end of every epoch by calling this function. Right? And this was a function we defined a little bit earlier, which was the root mean squared percentage error, first of all going e to the power of our sales, because our sales were originally logged. So this doesn't change the training at all. It's just something to print out. So we trained that for a while. And, you know, we've got some benefits that the original people that built this don't have. Specifically, we've got things like stochastic gradient descent with restarts. And so it's actually interesting to have a look and compare. Although our validation set isn't identical to the test set, it's very similar. It's a 2-week period that is at the end of the training data. So our numbers should be similar. And if we look at what we get, 0.097, and compare that to the leaderboard, public leaderboard, you can see we're kind of, let's have a look. In the top, actually, that's interesting. There's a big difference between the public and private leaderboard. It would have been right at the top of the private leaderboard, but only in the top 30 or 40 on the public leaderboard. So not quite sure, but you can see like we're certainly in the top end of this competition. I actually tried running the third place getters code, and their final result was over 0.1. So I actually think that we should be comparing to the private leaderboard, but I'm not sure. So anyway, so you can see there basically there's a technique for dealing with time series and structured data. And, you know, interestingly, the group that used this technique, they actually wrote a paper about it that's linked in this notebook. When you compare it to the folks that won this competition and came second, the other folks did way more feature engineering. Like the winners of this competition were actually subject matter experts in logistics sales forecasting, and so they had their own like code to create lots and lots of features. And talking to the folks at Pinterest who built their very similar model for recommendations for Pinterest, they said the same thing, which is that when they switched from gradient boosting machines to deep learning, they did like way less feature engineering. It was a much simpler model and requires much less maintenance. And so this is like one of the big benefits of using this approach to deep learning. You can get state-of-the-art results, but with a lot less work. Yes.
Are we using any time series in any of these fits?
Indirectly, absolutely. Using what we just saw, we have day of week, month of year, all that stuff are columns. And most of them are being treated as categories. So we're building a distributed representation of January. We're building a distributed representation of Sunday. We're building a distributed representation of Christmas. So we're not using any classic time series techniques. All we're doing is two fully connected layers in a neural net.
So through the embedded matrix, that's what the relationship.
Exactly. Yeah. So the embedding matrix is able to deal with this stuff like day of week periodicity and so forth in a way richer way than any standard time series technique I've ever come across.
And one last question.
Yeah.
The matrix in the earlier models, when we did the CNN, we did not pass it during the fit. We passed it when the data was, when we got the data.
So we're not passing anything to fit, just the learning rate and the number of cycles. In this case, we're passing in metrics because we want to print out some extra stuff. There is a difference in that we're calling data.getLearner. So with the imaging approach, we just go learner.trained and pass it the data. But for these kinds of models, in fact, for a lot of the models, the model that we build depends on the data. In this case, we actually need to know, like, what embedding matrices do we have and stuff like that. So in this case, it's actually the data object that creates the learner. So yeah, it is a bit upside down to what we've seen before.
I have a question.
Yeah.
So just to summarize, or maybe I'm confused. So in this case, what we are doing is like we have some kind of structured data. We did feature engineering. We got some columnar database or something similar.
A pandas data frame. Yep.
Yeah, data frame. And then we are mapping it to deep learning by using this
embedding matrix.
Embedding matrix.
For the categorical variables. For the continuous, we just put them straight in.
So all I need to do is like if I already have a feature engineering model, then to map it to deep learning, I just have to figure out which one I can move into categorical and then make it learn by itself.
Yeah, great question. So yes, exactly. If you want to use this on your own data set, step one is list the categorical variable names, list the continuous variable names, put it in a data frame, the pandas data frame. Step two is to create a list of which row indexes do you want in your validation set. Step three is to call this line of code using this exact, you can just copy and paste it. Step four is to create your list of how big you want each embedding matrix to be. And then step five is to call getLearner. You can use these exact parameters to start with. And if it overfits or underfits, you can fiddle with them. And then the final step is to call fit. So yeah, almost all of this code will be nearly identical.
I have a couple of questions. One is how is data augmentation can be used in this case? And the second one is what are dropouts doing in here?
Okay, so data augmentation, I have no idea. I mean, that's a really interesting question. I think it's got to be domain specific. I've never seen any paper or anybody in industry doing data augmentation with structured data in deep learning. So I think it can be done. I just haven't seen it done. What is dropout doing? Exactly the same as before. So at each point, we have the output of each of these linear layers is just a rank 1 tensor. And so dropout is going to go ahead and say, let's throw away half of the activations. And the very first dropout, embedding dropout, literally goes through the embedding matrix and says, let's throw away half the activations. That's it. Okay, let's take a break and let's come back at 8:05. Okay, thanks everybody. So now we're going to move into something equally exciting. Actually, before I do, I just mentioned I had a good question during the break, which was, what's the downside? Almost no one's using this. Why not? And basically, I think the answer is, as we discussed before, no one in academia almost is working on this because it's not something that people really publish on. And as a result, there haven't been really great examples where people could look at and say, oh, here's a technique that works well, so let's have our company implement it. But perhaps equally importantly, until now with this FastAI library, there hasn't been any way to do it conveniently. If you wanted to implement one of these models, you had to write all the custom code yourself. Whereas now, as we discussed, it's, it's basically a 6-step process, involving about, not much more than 6 lines of code. So the reason I mention this is to say, I think there are a lot of big commercial and scientific opportunities to use this to solve problems that previously haven't been solved very well before. So I'll be really interested to hear if some of you try this out, maybe on old Kaggle competitions, you might find oh, I would have won this if I'd used this technique. That would be interesting. Or if you've got some data set you work with at work, some kind of predictive model that you've been doing with a GBM or a random forest, does this help? The thing, I'm still somewhat new to this. I've been doing this for basically since the start of the year was when I started working on these structured deep learning models. So I haven't had enough opportunity to know where might it fail. It's worked for nearly everything I've tried it with so far. Yeah, I think this class is the first time that there's going to be more than half a dozen people in the world who actually are working on this. So I think, as a group, we're going to hopefully learn a lot and build some interesting things. And this would be a great thing if you're thinking of writing a post about something. Or here's an area that there's a post from Instacart about what they did. Pinterest has an O'Reilly AI video about what they did. That's about it. And there's 2 academic papers, both about Kaggle competition victories. One from Yoshua Bengio and his group. They won a taxi destination forecasting competition, and then also the one linked for this Rossmann competition. So, yeah, there's some background on that. All right. So language, natural language processing, is the area which is kind of the most up-and-coming area of deep learning. It's kind of 2 or 3 years behind computer vision in deep learning. It was kind of the second area that deep learning started getting really popular in. And, computer vision got to the point where it was the clear state of the art for most computer vision things, maybe in 2014, and in some things in 2012. In NLP, we're still at the point where for a lot of things, deep learning is now the state of the art, but not quite everything. But as you'll see, the state of kind of the software and some of the concepts is much less mature than it is for computer vision. So in general, none of the stuff we talk about after computer vision is going to be as settled as the computer vision stuff was. So NLP, one of the interesting things is in the last few months, some of the good ideas from computer vision have started to spread into NLP for the first time, and we've seen some really big advances. So a lot of the stuff you'll see in NLP is pretty new. So I'm going to start with a particular kind of NLP problem. And one of the things you'll find in NLP is like there are particular problems you can solve and they have particular names. And so there's a particular kind of problem in NLP called language modeling. And language modeling has a very specific definition. It means build a model where, given a few words of a sentence, can you predict what the next word is going to be? So if you're using your mobile phone and you're typing away and you press space and then it says like this is what the next word might be, like SwiftKey does this like really well. And SwiftKey actually uses deep learning for this. That's a language model. Okay, so it has a very specific meaning. When we say language modeling, we mean a model that can predict the next word of a sentence. So let me give you an example. I downloaded about 18 months worth of papers from arXiv. So for those of you that don't know it, arXiv is the most popular preprint server in this community and various others, and has lots of academic papers. And so I grabbed the abstracts and the topics for each. And so here's an example. So the category of this particular paper was CSNI is computer science and networking. And then the summary, so like the abstract of the paper, was saying the exploitation of wave bands is one of the key enabler for 5G mobile, blah, blah, blah. Okay, so here's like an example piece of text from my language model. So I trained a language model on this arXiv data set that I downloaded, and then I built a simple little test which basically you would pass it some like priming text. So you'd say like, oh, imagine you started reading a document that said category is computer science and networking, and the summary is algorithms that, and then I said, please write an arXiv abstract. So it said that if it's networking, algorithms that use the same network as a single node are not able to achieve the same performance as the traditional network-based routing algorithms. In this paper, we propose a novel routing scheme, blah, blah, blah. Okay, so it's learnt by reading arXiv papers that somebody who is saying algorithms that, where the word cat CSNI came before it, is going to talk like this. And remember, it started out not knowing English at all, right? It actually started out with an embedding matrix for every word in English that was random. Okay, and by reading lots of arXiv papers, it learnt what kind of words followed others. So then I tried, what if we said cat, computer science, computer vision, summary, algorithms that use the same data to perform image classification are increasingly being used to improve the performance of image classification algorithms. In this paper, we propose a novel method for image classification using a deep convolutional neural network, parentheses, CNN. So you can see, like, it's kind of like almost the same sentence as back here, but things have just changed into this world of computer vision rather than networking. So I tried something else, which is like, okay, category, computer vision, and then I created the world's shortest ever abstract, algorithms. And then I said title, on, and the title of this is going to be on the performance of deep learning for image classification. EOS is end of stream, so that's like end of title. What if it was networking, summary, algorithms, title, on the performance of wireless networks, as opposed to towards computer vision, towards a new approach to image classification, networking towards a new approach to the analysis of wireless networks. So, like, I find this mind-blowing, right? I started out with some random matrices, which are like literally no pre-trained anything. I fed it 18 months worth of arXiv articles, and it learnt not only how to write English pretty well, but also that after you say something's a convolutional neural network, you should then use parentheses to say what it's called. And furthermore, that the kinds of things people create algorithms for in computer vision are performing image classification, and in networking are achieving the same performance as traditional network-based routing algorithms. So, like, a language model can be like incredibly deep and subtle, right? And so we're going to try and build that. But actually, not because we care about this at all. We're going to build it because we're going to try and create a pre-trained model. What we're actually going to try and do is take IMDb movie reviews and figure out whether they're positive or negative. Right? So if you think about it, this is a lot like cats versus dogs. It's a classification algorithm. But rather than an image, we're going to have the text of a review. So I'd really like to use a pre-trained network. Like, I would at least like to start with a network that knows how to read English, right? And so my view was like, okay, to know how to read English means you should be able to like predict the next word of a sentence. So what if we pre-train a language model and then use that pre-trained language model and then, just like in computer vision, stick some new layers on the end and ask it, instead of to predicting the next word in a sentence, instead predict whether something is positive or negative. So when I started working on this was actually a new idea. Unfortunately, in the last couple of months I've been doing it, a couple of people have started publishing this. And so this has moved from being a totally new idea to being a, somewhat new idea. So this idea of creating a language model, making that the pre-trained model for a classification model, is what we're going to learn to do now. And so the idea is we're really kind of trying to leverage exactly what we learned in our computer vision work, which is how do we do fine-tuning to create powerful classification models. Yes, Jeanette?
So why don't you think that doing just directly what you want to do doesn't work better?
Because it doesn't. It just turns out it doesn't, empirically. And the reason it doesn't is a number of things. First of all, as we know, fine-tuning a pre-trained network is really powerful, right? So if we can get it to learn some related task first, then we can use all that information to try and help it on the second task. The other reason is IMDb movie reviews are, up to 1,000 words long. They're pretty big. And so after reading 1,000 words, knowing nothing about how English is structured or even what the concept of a word is, or punctuation or whatever, at the end of this 1,000 integers, they end up being integers, all you get is a 1 or a 0, positive or negative. And so trying to learn the entire structure of English and then how it expresses positive and negative sentiments from a single number is just too much to expect. So by building a language model first, we can try to build a neural network that kind of understands the English of movie reviews. And then we hope that some of the things it's learnt about are going to be useful in deciding whether something's a positive or a negative movie review. That's a great question. Can you pass that?
Thanks. Is this similar to the CAR-RNN by Karpathy?
Yeah, this is somewhat similar to CAR-RNN by Karpathy. So the famous CAR, as in CHAR, RNN, tried to predict the next letter, given a number of previous letters. Language models generally work at a word level. They don't have to. And doing things at a word level turns out to be, can be quite a bit more powerful. And we're going to focus on word level modeling in this course.
And then to what extent are these generated words actual copies of what it found in the training data set, or are these completely random things that it actually learned? And how do we know how to distinguish between those two?
Yeah, I mean, these are all good questions. The words are definitely words we've seen before, because it's not at a character level. So it can only give us the word it's seen before. The sentences, there's a number of kind of rigorous ways of doing it, but I think the easiest is to get a sense of here are two different categories where it's kind of created very similar concepts, but mixing them up in just the right way. It would be very hard to do what we've seen here just by spitting back things it's seen before. But you could, of course, actually go back and check, have you seen that sentence before? Or like a string distance, have you seen a similar sentence before? In this case, and of course, another way to do it is most importantly, when we train the language model, as we'll see, we'll have a validation set. And so we're trying to predict the next word of something it's never seen before. And so if it's good at doing that, it should be good at generating text. In this case, the purpose is not to generate text. That was just a fun example. And so I'm not really going to study that too much. But, you during the week totally can. Like, you can totally build your, Great American Novel Generator or whatever. There are actually some tricks to using language models to generate text that I'm not using here. They're pretty simple. We can talk about them on the forum if you like. But my focus is actually on classification, because I think that's the thing which is incredibly powerful. Like text classification, I don't know, you're a hedge fund, you want to read every article as soon as it comes out through Reuters or Twitter or whatever, and immediately identify things which in the past have caused, massive market drops. That's a classification model. Or you want to recognize all of the customer service queries which tend to be associated with people who leave who cancel their contracts in the next month. That's a classification problem. So it's a really powerful kind of thing for data journalism, activism, law, commerce, so forth, right? I'm trying to class documents into whether they're part of legal discovery or not part of legal discovery. Okay, so you get the idea. So in terms of stuff we're importing a few new things here. One of the bunch of things we're importing is Torch Text. Torch Text is PyTorch's NLP library. And so FastAI is designed to work hand in hand with Torch Text, as you'll see. And then there's a few text-specific subbits of FastAI that we'll be using. So we're going to be working with the IMDb large movie review data set. It's very, very well studied in academia. Lots and lots of people over the years have studied this data set. 50,000 reviews, highly polarized reviews, either positive or negative. Each one has been classified by sentiment. Okay, so we're going to try, first of all, however, to create a language model. So we're going to ignore the sentiment entirely. Right? So just like for dogs and cats, pre-train the model to do one thing and then fine-tune it to do something else. Because this kind of idea in NLP is so new, there's basically no models you can download for this, so we're going to have to create our own. Right. So having downloaded the data, you can use the link here. We do the usual stuff of saying the path to it, training and validation path. And as you can see, it looks pretty traditional compared to Vision. There's a directory of training. There's a directory of test. We don't actually have separate test and validation in this case. And just like in Vision, the training directory has a bunch of files in it. In this case, not representing images, but representing movie reviews. So we could cat one of those files, and here we learn about the classic Zombiegeddon movie. I have to say, with a name like Zombiegeddon and an atom bomb on the front cover, I was expecting a flat-out chop-socky fun coup. Rent it if you want to get stoned on a Friday night and laugh with your buddies. Don't rent it if you're an uptight weenie or want a zombie movie with lots of flesh eating. I think I'm going to enjoy Zombiegeddon. So, all right. So we've learned something today. All right, so we can just use standard Unix stuff to see how many words are in the data set. So in the training set, we've got 17.5 million words. Test set, we've got 5.6 million words. So here's this is IMDb. So IMDb is random people. This is not a New York Times listed review, as far as I know. Okay, so before we can do anything with text, we have to turn it into a list of tokens. A token is basically like a word, right? So we're going to try and turn this eventually into a list of numbers. So the first step is to turn it into a list of words. That's called tokenization in NLP. NLP has a huge lot of jargon that we'll learn over time. One thing that's a bit tricky, though, when we're doing tokenization is here I've tokenized that review and then joined it back up with spaces. And you'll see here that wasn't has become two tokens, which makes perfect sense, right? Wasn't is two things, right? Dot, dot, dot has become one token, right? Whereas lots of exclamation marks has become lots of tokens. So like a good tokenizer will do a good job of recognizing like pieces of an English sentence. Each separate piece of punctuation will be separated, and each part of a multi-part word will be separated as appropriate. So Spacey is I think it's an Australian developed piece of software actually that does lots of NLP stuff. It's got the best tokenizer I know, and so FastAI is designed to work well with the Spacey tokenizer as its torch text. So here's an example of tokenization. All right. So what we do with torch text is we basically have to start out by creating something called a field. And a field is a definition of how to pre-process some text. And so here's an example of the definition of a field. It says, I want to lowercase the text, and I want to tokenize it with the function called Spacey tokenize. Okay, so it hasn't done anything yet. We're just telling it, when we do something, this is what to do. And so that we're going to store that description of what to do in a thing called capital text. And so this is none of this is not FastAI specific at all. This is part of Torch Text. You can go to the Torch Text website, read the docs. There's not lots of docs yet. This is all very, very new. So probably the best information you'll find about it is in this lesson. But there's some more information on this site. All right. So what we can now do is go ahead and create the usual FastAI model data object. Okay. And so to create the model data object, we have to provide a few bits of information. We have to say what's the training set, so the path to the text files, the validation set, and the test set. In this case, just to keep things simple, I don't have a separate validation and test set, so I'm going to pass in the validation set for both of those two things. All right, so now we can create our model data object. As per usual, the first thing we give it is the path. The second thing we give it is the torch text field definition of how to pre-process that text. The third thing we give it is the dictionary or the list of all of the files we have, train, validation, test. As per usual, we can pass in a batch size. And then we've got a special couple of extra things here. One is very commonly used in NLP, minimum frequency. What this says is, in a moment, we're going to be replacing every one of these words with an integer, which basically will be a unique index for every word. And this basically says if there are any words that occur less than 10 times, just call it unknown, right? Don't think of it as a word. Right? We'll see that in more detail in a moment. And then we're going to see this in more detail as well. BPTT stands for back prop through time. And this is where we define how long a sentence will we stick on the GPU at once. So we're going to break them up. And in this case, we're going to break them up into sentences of 70 tokens or less on the whole. So we're going to see all this in a moment. All right. So after building our model data object, right, what it actually does is it's going to fill this text field with an additional attribute called vocab. And this is a really important NLP concept. I'm sorry, there's so many NLP concepts we just have to throw at you kind of quickly, but we'll see them a few times, right? Vocab is the vocabulary. And the vocabulary in NLP has a very specific meaning. It is, what is the list of unique words that appeared in this text? So every one of them is going to get a unique index. So let's take a look, right? Here is text.vocab.I to S. This is all torch text, not FastAI. Text.vocab.int to string maps the integer 0 to unknown, the integer 1 to padding, the integer 2 to the, then comma, dot, and, of, to, and so forth. Right? So this is the first 12 elements of the array of the vocab from the IMDb movie review. And it's been sorted by frequency, except for the first two special ones. So for example, we can then go backwards, S to I, string to int. Here is the, it's in position 0, 1, 2. So string to int the is 2. So the vocab lets us take a word and map it to an integer, or take an integer and map it to a word. Right? And so that means that we can then take the first 12 tokens, for example, of our text and turn them into 12 ints. So for example, here is of the, here you can see 7, 2, and here you can see 7, 2. Right? So we're going to be working in this form. Did you have a question? Yeah, could you pass that back there, you know?
Is it common to do any stemming or lemmatizing?
Not really, no. Generally, tokenization is what we want. Like with a language model, we, to keep it as general as possible, we want to know what's coming next. And so, like, whether it's future tense or past tense or plural or singular, like, we don't really know which things are going to be interesting and which aren't. It seems that it's generally best to kind of leave it alone as much as possible, be the short answer. Having said that, as I say, this is all pretty new. So if there are some particular areas that some researcher maybe has already discovered that some other kinds of pre-processing are helpful, I wouldn't be surprised not to know about it.
So when you're dealing with natural language, isn't context important?
Context is very important.
So if you're using the species tokenizer and literally just looking at individual words.
No, we're not looking at words. This is I just don't get some of the big premises of this. Like they're in order.
Oh, okay.
Yeah. So just because we replaced I with the number 12, these are still in that order. Yeah. There is a different way of dealing with natural language called bag of words. And bag of words, you do throw away the order and the context. And in the machine learning course, we'll be learning about working with bag of words representations. But my belief is that they are no longer useful, or on the verge of becoming no longer useful. We're starting to learn how to use deep learning to use context properly now. But it's kind of for the first time. It's really like only in the last few months. All right, so I mentioned that we've got two numbers, batch size and BPTT, backprop through time. So this is kind of subtle. So we've got some big, long piece of text. Okay, so we've got some big, long piece of text. Here's our sentence. It's a bunch of words, right? And actually what happens in a language model is, even though we have lots of movie reviews, they actually all get concatenated together into one big block of text, right? So it's basically predict the next word in this huge long thing, which is all of the IMDb movie reviews concatenated together. So this thing is, what did we say it was? Like tens of millions of words long. And so what we do is we split it up into batches first, right? So these are our splits into batches. Right? And so if we said we want a batch size of 64, we actually break the, whatever it was, 60 million words into just 64 sections. Right? And then we take each one of the 64 sections and we move it like underneath the previous one. I didn't do a great job of that, but right? Like move it underneath. So we end up with a matrix which is Actually, I think we move them crosswise, so it's actually, I think, just transpose it. We end up with a matrix that's like 64 columns wide, and the length, let's say the original was 64 million, right? Then the length is like 10 million long, right? So each of these represents 1/64th of our entire IMDb review set, right? And so that's our starting point. So then what we do is we then grab a little chunk of this at a time, and those chunk lengths are approximately equal to BPTT, which I think we had equal to 70. So we basically grab a little 70 long section, and that's the first thing we chuck into our GPU. That's a batch, right? So a batch is always of width 64, or batch size, and each bit is a sequence of length up to 70. So let me show you, right? So here, if I go take my train data loader, I don't know if you folks have tried playing with this yet, but you can take any data loader, wrap it with iter to turn it into an iterator, and then call next on it to grab a batch of data, just as if you were a neural net. You get exactly what the neural net gets. And you can see here, we get back a 75 by 64 tensor, right? So it's 64 wide, right? And I said it's approximately 70 high, but not exactly. And that's actually kind of interesting. A really neat trick that Torch Text does is they randomly change the backprop through time number every time. So each epoch, it's getting slightly different bits of text. This is kind of like in computer vision, we randomly shuffle the images. We can't randomly shuffle the words, right, because we need them to be in the right order. So instead, we randomly move their breakpoints a little bit. Okay, so this is the equivalent. So in other words, this this here is of length 75, right? There's an ellipsis in the middle. And that represents the first 75 words of the first review, right? Whereas this 75 here represents the first 75 words of the second of the 64 segments. Right? So you'd have to go in like 10 million words to find that one, right? And so here's the first 75 words of the last of those 64 segments, okay? And so then what we have down here is the next sequence, right? So 51, there's 51. 615, there's 615. 25, there's 25, right? And in this case, it actually is of the same size. It's also 75 by 64, but for minor technical reasons, it's been flattened out into a single vector. But basically, it's exactly the same as this matrix, but it's just moved down by 1, because we're trying to predict the next word, right? So that all happens for us, right? If we ask for, and this is the fast AI now, if you ask for a language model data object, then it's going to create these batches of batch size width by BPTT height bits of our language corpus, along with the same thing shuffled along by one word, right? And so we're always going to try and predict the next word.
So why don't you, instead of just arbitrarily choosing 64, why don't you choose like 64 is a large number, maybe like do it by sentences and make it a large number and then pad it with 0 or something. If you know, so that you actually have a one full sentence per line. Basically, wouldn't that make more sense?
Not really, because remember we're using columns, right? So each of our columns is of length about 10 million, right? So although it's true that those columns aren't always exactly finishing on a full stop, they're so damn long, we don't care. Because they're like 10 million long. right? And we're trying to also...
So each line contains multiple sentences.
Each column contains multiple sentences.
Sorry.
Yeah, it's of length about 10 million, and it contains many, 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 many sentences. Because remember, the first thing we did was to take the whole thing and split it into 64 groups. Okay, great. So I found this, pertaining to this question, this thing about like what's in this language model matrix, a little mind-bending for quite a while. So don't worry if it takes a while and you have to ask 1,000 questions on the forum. That's fine, right? But go back and listen to what I just said in this lecture again. Go back to that bit where I showed you splitting it up to 64 and moving them around, and try it with some sentences in Excel or something, and see if you can do a better job of explaining it than I did. Because this is like how Torch Text works. And then what FastAI adds on is this idea of like kind of how to build a language model out of it. Although actually a lot of that's stolen from Torch Text as well. Like there's sometimes where Torch Text starts and FastAI ends, or vice versa, is a little subtle. They really work closely together. Okay, so now that we have a model data object that can feed us batches, we can go ahead and create a model, right? And so in this case, we're going to create an embedding matrix. And our vocab, we can see how big our vocab was. Let's have a look back here. So we can see here in the model data object, there are 4,602 kind of pieces that we're going to go through. That's basically equal to the number of the total length of everything divided by batch size times BPTT. This one I wanted to show you. NT, I've got the definition up here. Number of unique tokens. NT is the number of tokens. That's the size of our vocab. So we've got 34,945 unique words. And notice they're unique words that had to appear at least 10 times. Okay? Because otherwise they've been replaced with unk. Right? The length of the data set is 1, because as far as a language model is concerned, there's only one thing, which is the whole corpus, right? And then that thing has, here it is, 20.6 million words in it, right? So those 34,945 things are used to create an embedding matrix of number of rows is equal to 34,945, right? And so the first one represents unk. The second one represents pad. The third one was dot. The fourth one was comma. Fifth one, I'm just guessing, was the, and so forth, right? And so each one of these gets an embedding vector. So this is literally identical to what we did before the break, right? This is a categorical variable. It's just a very high cardinality categorical variable. And furthermore, it's the only variable, right? This is pretty standard in NLP. You have a variable, which is a word, right? We have a single categorical variable, single column, basically, and it's a 34,945 cardinality categorical variable. And so we're going to create an embedding matrix for it. So M size is the size of the embedding vector, 200. Okay. So that's going to be length 200. A lot bigger than our previous embedding vectors. Not surprising, because a word has a lot more nuance to it than the concept of Sunday, right? Or Rossmann's Berlin store, or whatever, right? So it's generally an embedding size for a word will be somewhere between about 50 and about 600. Okay, so I've kind of gone somewhere in the middle. We then have to say, as per usual, how many activations do you want in your layers? So we're going to use 500. And then how many layers do you want in your neural net? We're going to use 3. Okay. This is a minor technical detail. It turns out that we're going to learn later about the Atom Optimizer. That basically the defaults for it don't work very well with these kinds of models, so we just have to change some of these. You know, basically any time you're doing NLP, you should probably include this line because it works pretty well. So having done that, we can now, again, take our model data object and grab a model out of it, and we can pass in a few different things. What optimization function do we want? How big an embedding do we want? How many activations, number of hidden, how many layers, and how much dropout of many different kinds. So this language model we're going to use is a very recent development called AWD-LSTM by Stephen Merity, who's an NLP researcher based in San Francisco. And his main contribution really was to show like how to put dropout all over the place in these NLP models. So we're not going to worry now. We'll do this in the last lecture, is worrying about like what is the architecture and what are all these dropouts. For now, just know it's the same as per usual. If you try to build an NLP model and you're underfitting, then decrease all of these dropouts. If you're overfitting, then increase all of these dropouts in roughly this ratio. Okay, that's my rule of thumb. And again, this is such a recent paper. Nobody else is working on this model anyway, so there's not a lot of guidance. But I've found these ratios work well. That's what Stephen's been using as well. There's another kind of way we can avoid overfitting that we'll talk about in the last class. Again, for now, this one actually works totally reliably, so all of your NLP models probably want this particular line of code. And then this one we're going to talk about at the end, last lecture as well. You can always include this. Basically what it says is when you look at your gradients and you multiply them by the learning rate, and you decide how much to update your weights by, this says clip them, like literally like don't let them be more than 0.3. And this is quite a cool little trick, right? Because like if your learning rate's pretty high and you kind of don't want to get in that situation we talked about where you're kind of got this kind of thing where you go, rather than little step, instead you go like, oh, too big, right? With gradient clipping, it kind of goes this far and it's like, oh my goodness, I'm going too far, I'll stop. Right? That's basically what gradient clipping does. Anyway, so these are a bunch of parameters. The details don't matter too much right now. You can just steal these. And then we can go ahead and call fit with exactly the same parameters as usual.
So, Jeremy, there are all these other word embedding things like Word2Vec and Glove.
Yeah.
So I have two questions about that. One is, how are those different from these? And the second question, why don't you initialize them with one of those?
Yeah. So basically, that's a great question. So basically, people have pre-trained these embedding matrices before to do various other tasks. They're not whole pre-trained models. They're just a pre-trained embedding matrix, and you can download them. And as Jeanette says, they have names like Word2Vec and Glove, and they're literally just a matrix. There's no reason we couldn't download them. Really, it's just like kind of, I found that building a whole pre-trained model in this way didn't seem to benefit much, if at all, from using pre-trained word vectors, whereas using a whole pre-trained language model made a much bigger difference. So like you remember what a big, those of you who saw Word2Vec, it made a big splash when it came out. I'm finding this technique of pre-trained language models seems much more powerful, basically. But I think we could combine both to make them a little better still. And you had a question.
What is the model that you have used? Like, how can I know the architecture of the model?
So we'll be learning about the model architecture in the last lesson. For now, it's a recurrent neural network using something called an LSTM, long short-term memory. Okay. So yeah, lots of details that we're skipping over, but you can do all this without any of those details. We go ahead and fit the model. I found that this language model took quite a while to fit, so I kind of like ran it for a while, noticed it was still underfitting, saved where it was up to, ran it a bit more with longer cycle length, saved it again, it still was kind of underfitting, ran it again, and kind of finally got to the point where it's like, honestly, I kind of ran out of patience. So I just like saved it at that point. And I did the same kind of test that we looked at before. So I was like, oh, it wasn't quite what I was expecting, but I really liked it anyway, the best. And then I was like, okay, let's see how that goes. The best performance was one in the movie where it was a little bit older. I was like, okay, it looks like the language model's working pretty well. So I've pre-trained a language model. And so now I want to use it, fine-tune it to do classification, sentiment classification. Now, obviously, if I'm going to use a pre-trained model, I need to use exactly the same vocab, right? The word "the" still needs to map to the number 2 so that I can look up the vector for "the," right? So that's why I first of all load back up my field object, the thing with the vocab in, right? Now, in this case, if I run it straight afterwards, this is unnecessary. It's already in memory, but this means I can come back to this later, right, in a new session, basically. I can then go ahead and say, okay, I've now got one more field, right? In addition to my field which represents the reviews, I've also got a field which represents the label, okay? And the details aren't too important here. Now this time I need to not treat the whole thing as one big piece of text, but every review is separate because each one has a different sentiment attached to it. Right? And it so happens that Torch Text already has a data set that does that for IMDb. So I just used IMDb built into Torch Text. So basically, once we've done all that, we end up with something where we can like grab, for a particular example, we can grab its label, positive, and here's some of the text. This is another great Tom Berenger movie, blah, 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 blah. All right. So this is all, nothing FastAI specific here. We'll come back to it in the last lecture, but Torch Text docs can help understand what's going on. All you need to know is that once you've used this special Torch Text thing called splits to grab a splits object, you can pass it straight into FastAI, text data from splits, and that basically converts a Torch Text object into a FastAI object we can train on. So as soon as you've done that, you can just go ahead and say, get model, right? And that gets us our learner. And then we can load into it the pre-trained model, the language model, right? And so we can now take that pre-trained language model and use the stuff that we're kind of familiar with, right? So we can make sure that, all except the last layer is frozen, train it a bit, unfreeze it, train it a bit. And the nice thing is, once you've got a pre-trained language model, it actually trains super fast. You can see here it's like a couple of minutes per epoch, and it only took me to get here's my best one here, it only took me like 10 epochs. So it's like 20 minutes to train this bit. It's really fast. And I ended up with 94.5%. So how good is 94.5%? Well, it so happens that actually one of Stephen Merity's colleagues, James Bradbury, recently created a paper looking at the state of, where they tried to create a new state of the art for a bunch of NLP things, and one of the things I looked at was IMDb, and they actually have here a list of the current world's best for IMDb, and even with stuff that is highly specialized for sentiment analysis, the best anybody had previously come up with was 94.1. So in other words, this technique, getting 94.5, is literally better than anybody has created in the world before, as far as we know, or as far as James Bradbury knows. So when I say there are big opportunities to use this, I mean this is a technique that nobody else currently has access to, which, you could whatever IBM has in Watson or whatever any big company has, that they're advertising, unless they have some secret source that they're not publishing, which they don't, right? Because people get if they have a better thing, they publish it. Then you now have access to a better text classification method than has ever existed before. So I really hope that, you can try this out and see how you go. There may be some things it works really well on and others that it doesn't work as well on. I don't know. I think this kind of sweet spot here that we had about 25,000, short to medium-sized documents. If you don't have at least that much text, it may be hard to train a decent language model. But having said that, there's a lot more we could do here, right? And we won't be able to do it in part 1 of this course. We'll do it in part 2. But for example, we could start training language models that look at lots and lots of medical journals. And then we could make a downloadable medical language model that then anybody could use to fine tune on a prostate cancer subset of medical literature, for instance. There's so much we could do. It's kind of exciting. And then, to Yannette's point, we could also combine this with pre-trained word vectors. So even without trying that hard, even without use, we could have pre-trained a Wikipedia, say, corpus language model, and then fine-tuned it into a IMDb language model, and then fine-tune that into an IMDb sentiment analysis model, and we would have got something better than this. So this, I really think this is the tip of the iceberg. And I was talking, there's a really fantastic researcher called Sebastian Ruder, who is basically the only NLP researcher I know who's been really, really writing a lot about pre-training and fine-tuning and transfer learning and NLP. And I was asking him, why isn't this happening more? And his view was it's because there isn't the software to make it easy, So I'm actually going to share this lecture with him tomorrow because, it feels like there's, hopefully going to be a lot of stuff coming out now that we're making it really easy to do this. Okay. We're kind of out of time, so what I'll do is I'll quickly look at collaborative filtering introduction, and then we'll finish it next time. But collaborative filtering, there's very, very little new to learn. We've basically learned everything we're going to need. So collaborative filtering, we'll cover this quite quickly next week, and then we're going to do a really deep dive into collaborative filtering next week. Where we're going to learn about, we're actually going to, from scratch, learn how to do stochastic gradient descent, how to create loss functions, how they work exactly, and then we'll go from there and we'll gradually build back up to really deeply understand what's going on in the structured models, and then what's going on in ConvNets, and then finally what's going on in recurrent neural networks, and hopefully we'll be able to build them all from scratch. Okay, so this is kind of going to be really important, this movie lens data set, because we're going to use it to learn a lot of really foundational theory and kind of math behind it. So the movie lens data set, this is basically what it looks like. It contains a bunch of ratings. It says user number 1 watched movie number 31, and they gave it a rating of 2.5 at this particular time. And then they watched movie 1029, and they gave it a rating of 3. And they watched movie 1172, and they gave it a rating of 4. Okay, and so forth. Right? So this is the ratings table. This is really the only one that matters. And our goal will be for some user we haven't seen before, for some user-movie combination we haven't seen before, we have to predict if they'll like it. Right? And so this is how recommendation systems are built. This is how Amazon decides what books to recommend, how Netflix decides what movies to recommend, and so forth. To make it more interesting, we'll also actually download a list of movies. So each movie, we're actually going to have the title. And so for that question earlier about what's actually going to be in these embedding matrices, how do we interpret them, we're actually going to be able to look and see how that's working. So basically, this is kind of what we're creating. This is kind of cross-tab of users by movies. Right? And so feel free to look ahead during the week. You'll see basically, as per usual, collab filter data set from CSV, model data.getLearner, learn.fit, and we're done. And you won't be surprised to hear when we then take that and we compare it to the benchmarks, it seems to be better than the benchmarks we looked at. So that'll basically be it. And then next week we'll have a deep dive and we'll see how to actually build this from scratch. All right. See you next week. Thank you.